If you're watching the frontier of artificial intelligence, you know the ultimate long-term goal isn't just building the biggest, fastest model. It's really about achieving true generalized intelligence AGI.
Right.
But AGI isn't just a destination. It's about the journey, and maybe more importantly, scoring high efficiently. For years, the road to AGI has felt blocked by this invisible wall, a crushing, almost exponential increase in resource consumption. It just made scaling these systems seem practically impossible.
That resourcing, that's exactly what we're digging into today.
Yeah.
We looked at sources detailing a really novel approach that seems to have fundamentally shattered that efficiency ceiling.
Okay.
We're diving into something called Efficient Evolutionary Program Synthesis, EEPS, and how it managed to achieve state-of-the-art performance on a critical benchmark, but while dramatically cutting resource costs, sometimes, by factors of 100 or even more.
Wow, okay. That's a bold claim. And you said it revolves around a specific target, the Abstract and Reasoning Corpus, or ARC-AGI benchmark. Why does ARC-AGI matter so much? What makes it, like, the ultimate test?
Well, ARC-AGI is explicitly designed to measure generalization, not just recall or pattern matching on scene data.
Right.
It presents the AI with totally novel tasks, these input-output grids of colored cells, and the system has to infer the underlying rule, the sort of program, that transforms the input into the output.
So it can't just rely on seeing billions of examples beforehand.
Exactly. It demands abstract reasoning, adaptive behavior, and the ability to figure out complex structural rules from very, very few examples. It's fundamentally different from the kind of tasks where, LLMs usually thrive, which often rely on predicting the next word based on massive training sets.
And the sources really hammer home just how difficult this benchmark is.
They really do. To give you a sense of the scale of the challenge, the average human scores around 77% on the first segment, ARC-AGI 1.
77%.
Yeah, and top human performers. They hit 98%, even 100%. Now compare that to leading AI models, even the biggest, most powerful LLMs available commercially. They just don't come close on these kinds of generalization tasks. Their performance on the full data set is often in the single digits.
Oof.
So when we talk about finding real human-like intelligence, ARC-AGI is currently maybe the most unforgiving litmus test we've got.
That definitely sets the stage. So let's look at the landscape before this breakthrough, the pre-EPS world. The existing state-of-the-art, you mentioned researchers like Jeremy Berman. What was the performance baseline there, and what was the big trade-off with that older generation of AGI search?
Right. So the baseline performance we're talking about came back in late 2020. Berman achieved 53.6% accuracy on ARC-AGI 1, which, was a huge jump at the time.
53.6, okay.
But the trade-off, and this was the primary weakness of that entire frontier approach, often called evolutionary test time compute, or ETTC, was its crippling inefficiency. It was just incredibly costly.
Explain that mechanism a bit. Why did ETTC, even if it works sometimes, get so expensive?
Well, ETTC systems are essentially brute force search mechanisms. They operate by maintaining this huge library of potential functions, like basic computational steps, and then they test literally trillions of combinations of these functions to see which sequence solves the current puzzle.
Trillions.
Yeah, the sources mention that systems used by some other groups, like Greenblatt's, could require searching through up to, say, 8,000 distinct Unix functions for each task just to synthesize one potential solution.
Wow. That sounds like just throwing massive compute power at every single problem until something eventually sticks.
Precisely. And the second major flaw was the lack of knowledge transfer. If an ETTC system successfully brute forced a solution for task A, the knowledge, the program it found, was rarely, if ever, abstracted or reused efficiently for task B.
So every task was like starting over.
Pretty much, yeah. Every single new task was solved virtually from scratch, which means the time and the money spent on the first task did very little to speed up or cheapen the second one.
And this cost problem just kept getting worse, right? The sources note that even Berman's own later research, when he was trying to push performance on the harder ARC-AGI-2 dataset, hit a really severe efficiency wall.
It absolutely did. He released a newer approach that did boost performance, I think, by about 14% on the more difficult set, which is good, but the cost consequences were just staggering.
How bad?
That new, higher scoring approach consumed resources roughly 3 times more on the easier ARC-AGI 1 tasks and an eye-watering 8 times more on the difficult ARC-AGI 2 tasks compared to his initial baseline.
8 times more expensive.
Yeah. This unsustainable resource consumption, that is the efficiency frontier that the authors of this EPS paper explicitly set out to break.
Okay, so given this crushing inefficiency, What was the key insight, the sort of aha moment the researchers had that allowed them to finally break free of this resource sink?
Yeah. The key realization, I think, was that AGI generalization probably requires hybrid intelligence. You need the, let's say, generative power of a large model, but you must pair it with a system that actually manages knowledge structure and enables reuse.
Okay, a hybrid approach.
Right. The innovation of EPS, efficient evolutionary program synthesis, is this deliberate and quite novel marriage of large language models, LLMs, with neurosymbolic program synthesis systems. Specifically, they integrated a system called DreamCoder.
Let's spend a moment on DreamCoder because it sounds like it's crucial for achieving this efficiency gain. What exactly is a neurosymbolic program synthesizer, and how does it store and reuse knowledge?
Okay, so DreamCoder uses what they call a wake-sleep algorithm. It's basically an iterative learning loop. Think of the wake phase as the active problem-solving part. The system tries to synthesize a program to solve the current grid puzzle.
Makes sense.
And when it succeeds, it has a working piece of code.
Okay, and the sleep phase, that sounds intriguing.
That's really where the efficiency magic happens. During the sleep phase, the system analyzes all the successful programs it's generated across various solved tasks, and it starts to abstract them.
Abstract, how?
It identifies common structural patterns, maybe shared loops or reusable subroutines. It then compresses these common patterns into more fundamental reusable programs or concepts, which get added to this growing library.
So instead of storing like 100 slightly different specific programs that do similar things, it figures out the core mechanism they share and stores that as a single concept.
Exactly right. So when the system faces a new puzzle, instead of searching from scratch using maybe 8,000 primitive functions like the old ways,
Right.
it first looks at its library of successful abstracted concepts, and that is the crucial mechanism that allows for genuine knowledge transfer across tasks, the very thing the older ETTC systems just couldn't do effectively.
But the author of EEPS didn't just plug DreamCoder in. They realized that while DreamCoder is great at managing knowledge, LLMs are incredibly powerful generators and maybe even planners. How did they merge the two without, forcing the LLM back into that inefficient, unstructured searching?
That's the really clever architectural novelty. They optimized the LLM prompt itself. They didn't just ask an LLM like Grok 4 or GPT-4o to generate code for this puzzle.
Okay, so the prompt engineering was key.
Hugely. When the LLM is given a new ARC-AGI puzzle, its prompt is heavily augmented. It gets contextual, highly curated information extracted directly from the DreamCoder library.
What kind of information? What's actually in that prompt?
Primarily three things. First, it gets access to the existing library of generalized programs, those successful concepts learned during the sleep phase.
The reusable building blocks.
Exactly. Second, it gets the best program found so far for the current task it's working on. And third, and this is critical, the system uses accuracy scores to weight the selection of which programs from the library to actually show the LLM. They call this score-weighted program selection.
That is fascinating.
Yeah.
So the LLM isn't just generating blindly in the dark. It's being actively nudged toward the highest performing conceptual building blocks that the system has already validated as useful.
It guides the search dramatically. Instead of this open-ended, massively inefficient search across the entire universe of possible code.
Which costs a fortune.
Right. The LLM is effectively leveraging maybe decades of prior work that the system has accumulated and compressed into this concise, reusable toolbox. This allows the powerful generative capability of the LLM to operate within the efficiency framework established by the neurosymbolic system DreamCoder.
So the key wasn't just solving the puzzle, but solving it using the tools they'd already built and refined. A completely different mindset from brute force. Okay, let's get to the impact. What were the results? Performance, yes, but maybe more importantly, the efficiency results.
The performance was stellar. Using Grok 4 as the LLM engine, the EEPS approach achieved 77.1% accuracy on ARC-AGI 1.
77.1%. Wait, that's basically the average human score on ARC-AGI 1, isn't it?
Statistically, yes. It's right there with the human average. And for the harder ARC-AGI 2, it hit 29.5%. That 77.1% on ARC-AGI 1 is a massive step forward for generalization capabilities in a single, efficient model.
Truly remarkable performance.
It really is, and the sources make it absolutely clear. While the raw score is fantastic, the defining success of this project is breaking that cost-performance Pareto frontier we talked about.
Right, the efficiency.
EPS achieved this human-level performance while being orders of magnitude more cost-effective than than those previous frontier models.
Okay, this is the moment for the listener to really grasp the economic shift here. Let's break down the specific cost comparisons per task based on the source material. How much did EEPS cost versus the others?
Okay, let's compare the cost of solving just one single task on ARC-AGI 1. The author's new EEPS solution cost only, get this, $2.56 per task.
$2.56. Wow, that makes this kind of research suddenly feel very accessible. Now, put that in perspective. What about the models that came before?
Okay, so Berman's highly optimized solution, the one that actually achieved a lower score than EPS, cost approximately $29 per task.
Okay, $2.56 versus $29. Still a big difference.
A huge difference. But then, if you look at the comparative models that relied more heavily on those massive brute force computational searches, like Greenblatt's, which we mentioned, tried to brute force a solution from that library of maybe 8,000 functions every single time.
Yeah.
That approach cost approximately $360 per task.
$460 per task, compared to $2.56. That's an astonishing difference. What is that? A factor of over 180 times more cost-effective than some of those prior attempts.
Exactly. The economic implications are just massive. This kind of cost reduction fundamentally changes the financial viability of doing AGI research.
How so?
Well, when your per-task costs drop that drastically, you can potentially transition from doing just a handful of really expensive, high-stakes experiments
Right, which limits progress.
to running maybe hundreds of thousands of cheap, repeatable experiments. This scalability is potentially what allows AGI systems to keep learning and improving without needing, the budget of a major government or a tech giant.
It really drives home that the path to AGI might not just be about building ever larger compute clusters, but about clever architecture, about smart organization of existing knowledge. Okay, so they've set this new benchmark for efficiency. Where does the source material suggest they're going next to push that cost envelope even further down?
The next planned phase involves pushing the efficiency of the recognition model. That's the part of the system that initially looks at the task, encodes it, and sort of suggests where the search for a solution should even begin.
Okay.
They plan to integrate a specific type of neural network called a latent program network, or LPN.
LPN. Okay, sounds technical.
Yeah.
Can you break down the goal of integrating this LPN? What does it actually do in simple terms?
Absolutely. So the LPN uses something called a variational autoencoder approach. But think of it this way. When DreamCoder is trying to find the best reusable concepts, it's searching in this huge, high-dimensional space of all possible programs. It's vast.
Okay.
The LPN's job is essentially to compress that massive space. It learns the underlying structure and finds, let's say, the zip file version of the program space.
Right.
It identifies the most efficient way to represent the important patterns.
So the LPN finds the most important compressed patterns within the program possibilities.
Precisely. By searching for solutions in this optimized latent space, this compressed representation, rather than the full, messy, inefficient program space.
It should be faster and cheaper.
Exactly. The LPN can significantly speed up the synthesis and selection process. This integration is designed explicitly to further optimize the selection of which learner programs to present to the LM, thereby pushing the computational cost even lower and maintaining that relentless focus on efficiency.
If we connect this back to the bigger picture, it feels like the real takeaway here is that true intelligence, or at least the path towards it, isn't just about raw complexity. It's maybe more about structured simplicity and effective reuse.
I think that's the core insight, yeah. The pursuit of AGI isn't just about hitting the highest score possible on a benchmark. It's about achieving that human-level generalization efficiently. EPS really demonstrates that by leveraging accumulated reusable concepts, those program libraries, and smartly guiding the powerful generative capabilities of LLMs, we can potentially solve some of the most complex generalization tasks without completely drowning in computational cost. This hybrid neurosymbolic approach is really proving to be, perhaps, the most viable path forward for resource-conscious AI development.
We've seen how leveraging existing knowledge, these structured concepts, can drastically cut the computational cost for genuinely novel problem solving. This shift away from pure brute force computation towards reusable concept-based reasoning, it changes the entire economics of intelligence research. So what does this all mean for you, listening right now? If a machine can be taught to generalize efficiently by reusing learned concepts, if the cost of abstract reasoning plummets from maybe hundreds of dollars per task down to mere dollars, what kind of high-stakes, historically expensive problems, maybe things like bespoke materials, science development, or large-scale drug discovery simulations, problems previously deemed just too computationally expensive, might suddenly be within practical reach? maybe even tomorrow.